Welcome to day 2 of calculus. We're going to start off by graphing two functions that, at least when written algebraically, look very different. You have our first one and our second one. So if we use our calculator to graph these two functions, and I've typed them in already, you end up with inputs that look like this. Notice I use the parentheses around the top and bottom of the rational function, but first I'm going to graph just x plus 5. And you notice the equal sign is turned on, so it's just graphing this function. So when I graph this, you end up with a linear function, a y-intercept of 5. That's great. So now I'm going to go back and I'm going to turn on this function by hitting enter on the equal sign and turning off this one by hitting enter there. So you'll notice that now just the bottom function is on. So when you graph this, you end up with, oh look, it's the same thing. Interesting. So in both cases, you end up with a graph that looks like this. How is that possible? Well, from your time in Algebra 2, you might be zoning in onto this quadratic. And you might think, oh, there's this great thing you can do to quadratics. You can factor them. So this is actually equal to x plus 3 times x plus 5. And just to remind you, how do you check to make sure that that's true? Well, you multiply it out. X squared plus 5x, 3x plus 15. Add the two central terms together. Okay, it does check. So now you can rewrite this rational function. Remember, it's a rational function because it's a polynomial over a polynomial. You now know that that's x plus 3 times x plus 5 over x plus 3. Oh, and now what cancels? The x plus 3's, meaning this is equal to x plus 5. This is equal to x plus 5. But the key element is that we canceled x plus 3. This is, without canceling the x plus 3, is the original rational function up here. You can't plug in a number. What's the one number you can't plug in? You can't plug in a number that makes the denominator x plus 3 equal to 0. And that's true when x is equal to negative 3. So when x is equal to negative 3, which is right here, x can't be that value. So in this case, when you're graphing this function, there's a hole right there. There's just one dot. And you can't really see it on your calculator graph because the resolution isn't too high on that graph. So if you did zoom in, you would eventually see a little pixel, empty pixel space. But the key thing to realize is that these two functions, when graphed, are identical except for 1 point and 1 point only. So we're going to launch into graphing rational functions. And it's a seemingly large process, but it's not that hard if you break it down into small steps. Our first step is going to be to factor both the numerator and the denominator. So first we have x squared plus 7x plus 12. And you might remember that you're looking for numbers that multiply together to get 12 and add together to get 7. Well, that's nice. X plus 3, x plus 4. Key side note, everything is factorable. Not everything is factorable nicely. Okay, what about 2x squared minus 5x minus 3? Now this is a bit trickier specifically because of this leading coefficient 2. So you know it's going to have to be 2x and x, and you might have to test this a bit. I still have to test things like this. Well, you know that the second two numbers have to multiply together to get negative 3, so just pick two of them and give it a try. So how about, I don't know, minus 3 and plus 1. Test it to make sure it works. You have 2x squared minus 6x plus x minus 3. Oh, did I get it right? Oh, I did. Yay, whoa me, go me. So on my first try I did it, but you could have guessed maybe you switched the 1 and the negative 3. You would have resulted in the wrong factorization, wrong factored form. So make sure you check it. So there's your factored form. So the factored form of y is going to be y is equal to x plus 3 times x plus 4 all over 2x plus 1 times x minus 3. So we factored it. Before you do anything else, you need to state the domain. And the domain is the set of all numbers that you can plug in. The set of all numbers that you can plug into a function. The set of all legal values, using air quotes again. So in this case, you're looking for the numbers that you can't plug in so you can take them away from all numbers. So find the numbers you can't plug in. And those are the numbers in this case that are going to make the denominator 2x plus 1 times x minus 3 equal to 0, because if the denominator is 0 right here, then you're dividing by 0. Note, we're not looking for any square roots of negatives because there's no radicals. Well, this is in a really nice form. It's two things multiplied together equals 0. So to make that true, either 2x plus 1 equals 0, or x minus 3 is equal to 0. So 2x equals negative 1, or x equals 3, and you have x equals negative a half. So you have two things here. X equals negative a half and x equals 3. Those are two numbers x can't be. So the domain is going to be the set of all x values such that x doesn't equal negative a half or 3. Another way to write that is all real numbers except negative 1/2 and 3. Another way to write it is negative infinity to negative 1/2 union negative 1/2 to 3 union 3 to infinity. That's all real numbers except negative a half and 3. Now, those are three different ways to write the same thing. I personally like the simplest one. At least I think it's that method. So remember that this little bar right here means such that. Or you could just write it out in words. Words is totally fine. So mathematicians like to write things real simple, and sometimes we can write them real complicated. It's all the same. So this is the domain. So if we go back and look what was asked, we just found the domain. For each restriction, state if you have a whole or as an asymptote. So let's look over here. We had these two domain restrictions, meaning x can't be negative a half or 3. We have to figure out, is it going to be an asymptote or is it going to be a whole in each case? Now, a whole only happens if you cancel at that value. You'll notice that nothing cancels here, so neither of them are going to be wholes. There's none of these terms cancel, so neither one of these are going to be wholes. So both are going to be asymptotes. Asymptote. You need to know how to spell that. So there's a step 3, which is going to be, is there anything to cancel? We already determined no. There's nothing to cancel in this case. For example, that could have been a +3 and then it would cancel, but there's nothing to cancel. If we canceled, it would make it a whole. If there would be wholes. Our step 4 is going to be to find the vertical asymptotes, and that's going to be where all the other restrictions are. In this case, both x equals negative a half and x equals 3. So we've gone a little bit beyond. We've determined that there's no holes in this one. This is an A, and it has two asymptotes, and in both cases they're vertical asymptotes, VA, vertical asymptotes. So let's do another practice one here. So again, the first step is going to be to factor. You're looking for two numbers that multiply together to negative 12, but add together to get 1, which is the coefficient of x, right there. So you end up with x, let's say +4 and x minus 3. I think that works. And then down here, hey, it's still another nice, quote-unquote, nice one to factor because the leading coefficient here is 1. Two numbers that multiply together to get negative 15, but add together to get 2. Let's try x minus x plus 5, x minus 3. That does work. So that was the first thing, factor. Do you remember the second? That's going to be to find the domain. Find the domain before you cancel. What can't you plug in? Look at the denominator. X can't be negative 5 or x can't be 3. So another way to say that would be the domain is x such that x cannot be negative 5 or 3. So next we need to see, is there anything that's going to cancel? Is there anything that's going to cancel? Well, in this case, something does cancel, the x minus 3. So that means there's going to be a whole when x equals 3. Whole when x equals 3. Excellent. Now, we didn't find the point where that's true. If we wanted to find the point where that's true, you have to plug 3 into what's left. Where is the whole going to be? The whole is going to be when x is equal to 3. So it's going to be 3 plus 4 from here over 3 plus 5. That's going to be 7 over 8. So the whole will happen at hole at the x value of 3 and the y value of 7/8. It's going a little bit further than the question asked, but that's where the hole is. Now, where's the vertical asymptote going to occur? Well, that's at the other x value that didn't cancel. That's this one right here. This one, yay, x equals -5. So the vertical asymptote, x equals -5. That's a vertical line at x equals -5. So now we're going to put together everything we've learned about rational functions, add in a few more things, and then graph them from a function. So first we're going to state the end behaviors. And remember, that's the limit as x goes to infinity of the function and the limit as x goes to -infinity. What happens as x gets infinitely big, infinitely small, or infinitely big and negative? So let's start with this one. What happens as x goes to infinity of this function? So remember, infinity is a concept, not a number. It's infinitely big. So when you're plugging something infinitely big into this expression, what are the only terms that are really going to matter? Meaning, which terms are going to get so large that the other ones are going to be infinitesimally small? Well, those are going to be the terms that contain x squared, because x squared is going to get so much bigger than everything that has a lower power. So everything here really is going to get infinitesimally small in comparison to those two things. So this limit right here is going to be equal to what happens as x gets really, really big, to 2x squared over x squared. And in that case, it cancels, so it's 2. So as x gets infinitely big, it gets infinitely close to 2. Well, as you go to -infinity, we're going to negative, we're going to the left this time. The same thing is true. These two terms are the biggest ones, the ones with the highest power. So in this case, it will still equal 2x squared over x squared. Squaring things, they're going to cancel again. It'll be 2. Now you'll notice that we didn't say, does it approach from above or below? Above or below 2. Let's leave that till a little bit later, but we know that as x gets infinitely big, the function approaches 2. And as x gets infinitely big and negative, it approaches 2. We're not quite sure which side of 2 it approaches on, but we'll figure that out later. So let's find the domain and state holes or asymptotes. So remember, to find the domain, the first thing we have to do is factor. So the factored form, we're trying to factor this. So the top is a little tricky because it has a leading coefficient of 2. But let's try to factor it. So we're looking for things, we can test it a little bit here. Let's try, how about, I don't know, -4 and +3. Let's see if that works. So if we test that out, you end up with 2x squared minus 8x plus 3x minus 12. Well, we have the minus 12, but when you add these together, you get -5x. So that's not correct. Okay, so we're pretty close here. What about, I don't know, -6 and 2. 2x squared minus 12x plus 2x minus 12. Well, that's definitely not -2x. So that didn't work. So what are other two numbers that could multiply together to get -12? We could reverse it. How about, I don't know, -4 and +3? So that's going to be 2x squared plus 6x minus 4x minus 12. Oh, it's really close. It's +2x. So if you get a sign difference like that, all you need to do is change the middle sign. So it's going to be minus, so it's going to be +3 here. Oh, is that what we had before? So it's going to be -3 and +4. We test that, you get 2x squared minus 6x plus 4x minus 12. Oh, that is -2x. So we found the right one. I did that out to demonstrate that factoring still takes time. And one thing I did there that you don't actually want to do is keep on erasing what you test. Keep a record of what you test, or it's hard to remember what you tested. So let's factor the denominator. It's going to be x and x. And then 15, and it's negative, but it's possible. I think it's going to be -5 and -3. That does work. So remember, you find the domain before you cancel. And in this case, you look at, remember, the denominator. What can't you plug in? Well, x can't be -3 and x can't be 5. So the domain is going to be x such that x does not equal -3 or 5. There's your domain. But we want to know, are they holes or asymptotes? Now that has to do with whether you cancel. Well, hey, look, it does cancel. So the one you canceled, this is going to be a whole, and this one's going to be a vertical asymptote at x equals 5. Yay. Finding intercepts. Finding intercepts. The x-intercept is when y equals 0. So that's the output. So you can take the simplified form of the output, and that's going to be 2x plus 4 over x minus 5, and you set that equal to 0. One way to think about this is the only way to make a fraction equal to 0 is to make the numerator equal 0. So that's going to be 2x is equal to negative 4. So x is equal to negative 2. So that right there is the x value for the x-intercept. So the point is going to be negative 2, 0. That is your x-intercept. So what about your y-intercept? Your y-intercept is when x is equal to 0. So you just plug 0 into this. So you get 2 times 0 plus 4 over 0 minus 5 is 4 over negative 5. Remember, that's a that is the y value of the y-intercept. So the point is going to be 0 comma 4 over negative 5, or negative 4/5. So that right there is your y-intercept. Yay. So the last thing we're going to do here is we're going to find out or figure out what happens when x goes to 5 from the right and x goes to 5 from the left. So you can think of it as a number really close to 5 in this case right here. Let's look at I first here. As x is really close to 5 from the right, it's going to be a little greater than 5. So one way you can think about that is plugging in something really close, so maybe like 5.1. So if you do that, so like f of 5.1, it's going to be 2 times 5.1 plus 4 over 5.1 minus 5. So this right here, you get 10.2 plus 4 is going to be 14.2, and this right here is going to be 0.1. So it's 14.2 over 0.1. So that's going to be a big number divided by a small number, really small number, 0.1. So this actually comes out to be, if you did this out algebraically, if you did this whole thing out algebraically, you would end up with 14.2 over 0.1, which is 142. What happens if you got even closer to 5 from the right? So 5.01, well, you're going to get 1,420. 5.001, 14,200. This is getting infinitely big and positive. So the answer here is going to be positive infinity. Positive infinity. Let's go over here. Remember, we're looking at 2x plus 4 over x minus 5. What happens as you what happens to the output as you approach 5 from the left, meaning something like 4.9999999? Well, you're still going to end up with something on top around 14, really close to 14. But if you plug in 4.999999, something small, you're going to get negative 0.0000 as far as you want 1. Well, that 14, when you divide it here, is going to be 14 lots of zeros, right? But it'll be negative. So in this case, it's negative infinity. So the end behaviors tell us that, excuse me, not end behaviors. As you approach 5 from the right, it goes to infinity. And as you approach 5 from the left, you get negative infinity. One thing that's important to note is an error right there. That should be a 2. You might have noticed that. So now we have done piece by piece and found a bunch of things. We found end behavior here. We found holes and asymptotes, intercepts right there. And we found what happens as you approach 5 from the left and right. So now let's put it all together in this graph. So first, we know that the end behaviors, as x gets infinitely big, it approaches 2. And as x gets infinitely big and negative, it approaches 2. So that means on this graph, we need to put in a horizontal asymptote right here at 2. So we know that the function will approach y equals 2 as x gets infinitely big and small. We don't know what side it will be from. And then there is a vertical asymptote at 5. And there's a vertical asymptote at 5 because we couldn't plug in 5. Remember that? X equals 5. So the vertical asymptote comes from right here in the middle where we knew that from this 5, you can't plug in 5 and it doesn't cancel. So there's our vertical asymptotes. So once you plot your asymptotes, plot your intercepts. So first do your asymptotes and then do your intercepts. This tells you a whole lot. So we know from here, where were our intercepts? Let's find them here. We know there's one at -2, 0, and 0, -4/5. So -2, 0 is right here. And -4/5 is going to be right about there. So what will this look like? Well, we know that these two points are going to be connected. So it's going to be curved, kind of like this. And we also know we have some end behaviors. The limit as x goes to 5 from the left was -infinity. So as it approaches from the left, it's going to go infinitely down. So that means that this has to go down like this. And if that's true, so this is going to keep going up because it doesn't have any more intercepts. There it is. Yay, we're almost done. But we also know the limit as x goes to 5 from the right was +infinity from earlier. So as you approach 5 from the right, it goes infinitely up. So we know the curve is going to go up. So therefore it's going to go down like this. It's going to go down like this. Now we need to plot the hole. The hole happens, where was it? The hole was at x equals 3, right? There's a hole at x equals, sorry, -3. X equals -3. So for wherever this function is -3, wherever it is -3, oh, I just noticed an error here. It's not x equals -3, it's x equals 3. Because x minus 3 equals 0, x should be 3. So that should be +3 right there. Little mistakes. So we go down here, where's 3? 3 is right about here. So there's a hole right there. So that's what it could look like. What do we have? We have our end behaviors right here and here. We have our intercepts. We have our hole. And we have our asymptotes, the vertical and horizontal. So it's a lot to put together, but if you do each piece, so state the end behaviors, domain, intercepts, and then you evaluate around the vertical asymptotes, you can put it all together carefully into a picture.